better. This game very oh god damn it. My record's
Testing. Okay.
Huh. I just downloaded it.
Okay.
So.
Okay. So we're gonna get started here. We're going to be continuing on from where we dropped off last time. And in today's class, I'm going to be going over, really update this so it's not confusing when you view it online. I'm going to be going over a couple of things that build on some of what we saw last time. We're going to continue to talk about nonlinear models, and we're going to explore a little bit more detail some of the features that make them nonlinear, both from sort of the equations perspective and the perspective of their behavior when we consider the interactions between different people within the model. And then we're going to try to look at a stock and flow perspective, try to give a stock and flow perspective on why we see the certain behavior coming out of these models that we saw last time. I'm also going to be talking about a set of notations and intuitions that lay behind these models to help better understand that behavior. This understanding will carry over to not only the next lecture or so, but also for our discussion of agent-based models starting next week. Okay, so today we're going to be continuing on this theme of nonlinearity in aggregate system dynamics models and going into it in a little bit more detail. We saw last time how we could characterize infection spread within a population in a simple way by dividing up the population into several categories. And the categories we used last time were very widespread. It reflected a very widespread way of characterizing the situation, dividing people up into susceptibles, infectious individuals, and removed, where the infectious individuals are simultaneously both infected and infective. That is, they're infected by the infection, presumably suffering in many cases adverse effects, but they're also able to spread that infection. And this division harks back to the work of Kendrick and McCormick back in the 1920s. So it's a very established way of analyzing systems involving spread of infectious disease. However, while we use this to characterize infectious diseases classically, this same formulation, the same basic mathematics, the same basic stock and flow structure, has been used to characterize a wide variety of other phenomena that spread by a process that might be known as contagion. Can anyone here characterize a few other processes besides spread of pathogen that might also exhibit the sort of contagion, the sort of behavior where someone who becomes infective, and I'll use that in scare quotes there, is therefore more likely to pass it on to another person. A case serves as a risk factor for another case. Could anyone give me some other types of phenomena that spread via contagion?
Software, especially those with social components.
Okay, great. Yeah, exactly. So, for example, whether you're a member of Facebook or whether you join Twitter, in fact, your likelihood of retweeting a message, right? So propagation of messages and information, as well as sort of joining those systems. If members of your social network are very well represented on, be it Twitter or Facebook, you're more likely to join yourself. So your adoption behavior of social media, your adoption behavior of social software, social computing software, and also your behavior on it is often shaped in this sort of way. How about other phenomena? Yeah. Rumors. Yeah, spread of rumors. Someone hears the rumor, finds it intriguing, may pass it on, right? Gossip works very much that way. Others? Well, companies bet a lot on this for adoption of products. In fact, that's why they're so well represented these days in the social media space. They hope that that things will go viral, that you'll be raving about the new gadget you got, and you'll spread that news to others, and they'll go out and buy it. So there's a very conscious attempt to encourage contagion when it comes to adoption of new products. And indeed, adoption of technologies, innovation has been studied using this sort of framework. So SIR model, well, we'll be talking about it in terms of an infectious context. A lot of what we'll be talking about today in terms of the basic dynamics, what we see over time in these sort of systems, will carry over to diverse domains. We'll see the same basic dynamics in case after case after case, quite aside from spread of an actual pathogen. Okay. So the basic sort of model that we had formulated had susceptible, infected, and recovered. It had this force of infection. Can anyone remind me what that represented? What's the force of infection? It's a key quantity in these models.
The likelihood that a susceptible would become infected?
Yeah, per unit time. Yeah, exactly. So it's a chance per unit time. Could be greater than 1. If it was greater than 1, it would just mean their average time remaining in the susceptible state would be less than 1. Yeah, exactly. So it's not a probability, it's probably density. It's a probability per unit time. And it's one of the distinguishing features of the nonlinearity of this model. The fact that force of infection is not a constant as it would be in a first order delay, where you have a certain chance per unit time of leaving. It's instead varying with the number of infectives and the fraction, in fact, of the infectives that are in the population. Now, one of my purposes in this lecture is to introduce a brief notation for characterizing models like this that will allude to their underlying mathematical structure. So we have suppose we have a structure like this. When we want to characterize it mathematically, when we want to write down the equations to reason about them, we often want to use shorter names. So while a model like this, for good software engineering reason, uses names that are readily recognizable, that can be less likely to be misunderstood, when we want to characterize it mathematically, we use a shorthand notation. We make use of brief names for stocks. Here, English letters S, I, and R. And then we denote various parameter values, things like context per susceptible. Instead of talking about context per susceptible, we talk about C. It's some number of people per unit time you're meeting up, right? Beta, this chance that if a susceptible meets an infective, what's that chance there'll be a transmission? We call that beta. These are time-honored names. If you talk with someone in this field and you talk about beta, they'll know what you mean, or C, know what you mean. So we give these short names, and then we're going to go and actually write down the equations associated with this. And the equations for this sort of model that can be written down for this model can be crisply described by the framework known as ordinary differential equations, or state equations. They're also called very commonly. They go by various names. Unfortunately, the color here is being captured quite poorly. What appears on my screen, and indeed on this screen before me, as red over here is turning out as sort of a purplish color. And this is a nice navy blue on mine, but it's turning into a color that whose blueness is less than its redness. So these are the corresponding equations, and I was hoping those colors would come through nicer. What corresponds to what? Well, let's take this case of this recovery. What's the formula, ladies and gentlemen, for the recovery here? What would be the expression that would go in recovery? This is a first-order delay. Mu is a delay. It's a mean time with disease, as we'd see there, the average duration of infectiousness. So what would the formula be here? If that's a time, and this is people, and this is a flow measured as people per unit time, what is the formula for this got to be? What? Sorry? Yeah, infective over average. And you'll see it right here, okay? That's what that is. This term over here, this key term that we reasoned through last time, which we'll come back to, is located here. What we have here on the left-hand sides are what? Who, perhaps from a physics background, will recognize these treasured quantities on the left? Yeah. The derivatives with respect to time, written in a notation that dates back to Leibniz. So S dot means the rate of change of S per unit time, how quickly it's increasing, or if it's negative, decreasing. I dot, rate of change in I, how quickly it's increasing or decreasing, R dot. So if I dot is 5 and time units are measured in days, then for each successive day, the number of infected people will go up by 5. So we can write this equation in this form, and fundamentally we're describing how the rates of change of the system, how S's rate of change, or I's rate of change, or R's rate of change, depends on the state variables of the system. Looked at another way, ladies and gentlemen, these things on the right are nothing more than less than the net flows over here. So let's take I, for example. Let's take S. We have a flow of M coming in for the number of cases of immigrants, and we have this flow going out, which we derived last time. Can anyone reason through for me, what does this flow represent? I argued last time this is the heart of an infectious disease model. And can anyone help me reason through?
Total number of susceptibles infected per unit time. That's contact.
Good. That's right. So this quantity gives the number of susceptibles infected per unit time. Remember, where you have contact C with maybe it's 100 people per day, right? Of those, I over N. What does I over N intuitively represent? The prevalence of infection, the fraction of the entire population that's infected. I should say here, N is S plus I plus R, right? So this is the fraction of the entire population that's infected, I over N. C times I over N, that 100 people per day I'm meeting up. Suppose 50% of the population's infected, then I'm meeting up on average with C times I over N, that is 50 people per day, right? 100 times 50%. And then beta is what? Transmission for a given contact between a susceptible and an infective. So for each of those 50 people, I have a 1% chance of getting infected, say, right, for each of those contacts. Okay, so that was the formula we wrote. You'll notice that this flow, it's a flow out of S, hence it's connected with S with a minus sign. If that flow is faster, S will be decreasing faster, be drawn down. The rate of change of S, which is given by M minus this, that's the net flow into S. This flow in minus this flow out, it gives the net flow. That net flow will tend to be smaller the bigger and bigger this is. At some point it will go negative, it will be drawn down, right? You'll notice the same flow flows into I. That's the nature of flows. If it's flowing from S to I, there's a conservation involved. So all these folks that leave S have to come into I. Similarly, what does this flow represent? I over mu. Where can I find that on the diagram? I alluded to it earlier. Sorry? Yeah, so it's recovery. That flow flows out of I, and it flows into R, right? Hence, this minus, right? Again, this is the net flow into I, right? Remember, isostock, it changes only by virtue of the flows. How quickly it changes is dictated by the value of those flows. If the flow out is 10 people per unit time and flow in is 0, it's going down by 10 people per unit time, say per day, right? So I's value, the rate of change of I, as given by this I dot here, is just given by the net flow, the rate of net flow. This flow in, that flow out. Does that make sense to people? I know for some people, probably, know this in your sleep. For some people, this may be totally new. So I'm trying to do a gentle introduction to this sort of notation, which it turns out will be really useful for a few tasks that we'll talk about a bit later. Okay? In system dynamics modeling, we don't need to look at these equations all the time, but if you have comfort with them, you can do some really neat stuff, particularly in terms of analyzing how the model can behave. You can figure out things like where its points of equilibrium. Are those stable, for example, using this sort of notation? Okay, so here we have a characterization of the same system using differential equations. And this is one of the strengths of system dynamics. If you wish to seek recourse to the underlying mathematics, there's this whole edifice of applied mathematics built around state equations, differential equations like this. There's thousands of books about how to analyze these and gain insight in various forms. How to analyze, for example, under what values of beta will a certain fixed point still be stable? Under what point, under what conditions will the system quickly enough treat cases that the infection never gets established, even if someone were to come into Saskatoon with the disease. So, having recourse to this is useful. What I want to highlight here, folks, is nonlinearity. So where's the nonlinearity here? Well, at a symbolic level, you can recognize this nonlinearity because it's nonlinear with respect to these state variables. There's an I times an S here. Do you see that? All right? Rearranging, you could see it more clearly. Is this SI, right? I just rearranged these equations to bring them next to each other. And we have this nonlinearity here. It starts to matter not just how many people there are in S, but how many people there are in I in terms of that particular flow. So that's one way to view the nonlinearity in this system. And that's fine. You can view it at that symbolic level. It's nonlinear with respect to these state variables. We can't consider... Okay, another way to view this is from a standpoint of so-called superposition. Here, the idea is, I noted last time, the system is linear with respect to some input, in this case, say, initial values of stocks. If the response of the system to the input is simply the sum of the response of the system with respect to various pieces of the input. If you could take the input apart, so you have an input of a certain number of people who are initially in each stock, and if you could consider a bunch of scenarios where you consider them with respect to just the people in this stock, and So you only have people in this stock. You only have people in this other stock. You only have people in that other stock. If you can figure out the system's responses to each of those and sum them up, and if that's the system's response to having people, all those people across all these different stocks, then that's a linear system. A linear system will have that property. We can, if we have some input, some arbitrary input, we can break it up into pieces. Pieces that are simple to analyze those pieces, and we know how it responds to the whole system. But with a nonlinear system, we can't do that. And I want to show you this difference, okay? I want to give you a sense of this difference. Okay, so so I just created this before class. Here's a simple, reasonably simple, a little bit textured, linear system. Now, this system, I deliberately designed it so it would exhibit some properties that are not trivial. So we have here, for example, a birth rate, which applies to the total population. So this is some birth rate, say a 2% birth rate. That would mean, for every 100 people in the population, there's 2 babies per year, right? So here we have a birth rate, and what do you think the formula for the number of births is per year? If the birth rate is measured in 1 over years. Births would be birth rate times the total population, right? Good. And then we have 2 first-order delays with competing, we have two first-order delays, one there. This one has some competing risks. And this is all linear in the sense that incidence is just the diabetes incidence rate times the number of non-diabetics. Non-diabetic mortality is just some non-diabetic mortality rate times the number of non-diabetics. Diabetic mortality is just some diabetic mortality rate times the number of diabetics. Okay? So we can characterize a situation like this, and its behavior over time is kind of interesting. We have what sort of feedbacks in this system? What sort of feedbacks are in the system? Are there any feedbacks in the system?
Other than birth rate and total population.
Okay, so birth rate, is there a feedback here?
The number of births, as they become more people, there'll be more people being born.
Okay, what sort of feedback is that? Positive feedback. It's divergent. You start with 200 initial people versus 1 initial person. The difference between those 2 scenarios, okay, maybe not 1 initial, maybe we'll start with 2. Because people here don't bud. Normally it takes 2 to have a birth. So suppose we start with 2 initial people versus 2,000. And we start with those 2 scenarios. If we consider those scenarios over time, are they going to get closer together over time or more divergent over time? They're actually get further and further apart. The one with 2,000, they're both going to be growing exponentially, but the gap between them is going to be widening. It's not just a gap of about 2,000 people or 1998 people. It's going to be growing. Okay, so there's a positive feedback there. It's unstable and magnifies differences. Okay, are there negative feedbacks here?
The non-diabetic incidents.
Okay, yeah, so there's a negative feedback here. There better be a negative feedback, because if there's none of the non-diabetics, if this is 0, then there's going to be no one to go out these flows, right? So these flows here are leaving the stock, and if they had no negative feedback here, they would drain this to go negative. If they didn't care about the value of non-diabetics, it would just go negative. So hopefully these flows will be smaller and smaller and smaller, depending on as the number of non-diabetics becomes smaller. And indeed, with a first-order delay, you see that. The formula for this, if we have a certain chance per unit time of becoming diabetic, what's the formula for incidence here? It's this chance per unit time times the number of non-diabetics. Is that a negative feedback? Yes, it is. It's staring me in the face right there. Let me trace it for you. So non-diabetics to incidence. As the number of non-diabetics goes up, does incidence tend to go up? So we know that the number of cases per year, does it tend to go up or down as the number of non-diabetics goes up? Up. And as the incidence goes up, as the number of cases per year goes up, does the number of non-diabetics go up or down? Down. So there's a negative feedback involving this. There's a negative feedback involving this. There's a negative feedback involving this guy here. Excuse me, like that. So there's negative feedbacks here. This is not a totally trivial system. There's actually quite a few small feedbacks. There's 1, 2, 3, 4. And for those who are interested, it turns out in the underlying symbolic math, you can identify feedbacks associated with eigenvalues of the system, and there's some really neat stuff you can do with that sort of knowledge, and eigenvalue type analysis, particularly around certain points. But we won't be covering that here. Let's talk, though, about the corresponding differential equations for this. These are the equations for this same system written out. So we, again, have a flow in to non-diabetics, right? And that flow in is given by some birth rate times the total population, n plus d. Remember what I said when I first introduced these formulas, these auxiliaries. I said that from a mathematical standpoint, they collapse out. They're actually not mathematical quantities so much as software engineering quantities. They're quantities that allow us for human use rather than mathematical use. Total population here is nothing more than n plus d. Wherever it's used, you just substitute this. So n dot equals alpha times n plus d. This is the total population, right? Omega n is just the mortality rate for non-diabetics. And this is associated with incidence of diabetes. So we have some delta, this diabetes incidence rate times non-diabetics, and it's flowing into diabetics here. And then we have minus WD, this omega d rather. So the rate of mortality for diabetics times the number of diabetics. Are people comfortable with that? Translating this into this form. You may wonder why I'm having you do this. Well, it turns out it'll be very useful shortly. Okay. And you should realize that it turns out for certain types of questions, it's extremely powerful to be able to do this, and it's useful to not, know how to read these sort of things and parse them into a stock and flow diagram, because sometimes you'll see models stated like this. Okay, but in terms of nonlinearity, let's see the implications. Ladies and gentlemen, suppose that I were, within this model, to place 1,000 people in the non-diabetic category. Well, suppose I'm interested in a situation where we have initially 1,000 people in the non-diabetic stock and 1,000 people in the diabetic stock, and I want to see how the system responds. I want to run a scenario, 1,000 people diabetic, 1,000 people non-diabetic, and I want to see how it responds, right? I want to see what the resulting output is. Well, turns out this system is linear. If you look at its analysis here, you don't see any situation where you have multiplications of the two-state variables, n times d. You see n plus d, but no n times d. And that tells us it's linear here. So we can actually do this analysis just directly. 1,000 non-diabetics, 1,000 diabetics. If we want to know what that is, we could analyze non-diabetics, 1,000 of them, and 0 diabetics. And here's 1,000 non-diabetics, and here's 0 diabetics initially. And we could have another scenario where we start with 1,000 diabetics and 0 non-diabetics. And we could end up with a situation where we get a result, if we total those up, which is the same exactly as if we simulated the full system with 1,000 of one and 1,000 of the other. It's a linear system. We want to analyze its response to having 1,000 here and 1,000 here. We just have to break it up into 1,000 only here and 0 here, and 1,000 only here, 0 here, and simulate each of those, and we know its response to the combined situation. It's completely transparent. Okay, that's a linear model. And that allows us, from the standpoint of analysis, we can do all sorts of neat things about characterizing fancy situations into their pieces. It allows us to actually avoid simulating them. For many types of analyses, we just don't simulate them. We just know ahead of time what the behavior will be. We could figure it out in closed form, analytically is the term we used. So that's great, but now let's talk about an SIR model. What's different here? What's different here? I said it was nonlinear, but that was with respect to this symbolic stuff. I mean, at a basic level, there's an intuition that goes beyond just the fact we're multiplying two stocks. Okay, it goes beyond this. Specifically, if with the SIR model we examined a situation where we have 1,000. Suppose we want to understand the result of a situation where we start with 1,000 susceptibles, 1 infective, and we want to know what the result is. Well, we might think naively, well, let's break it up into those pieces. Only with 1,000 susceptibles, let's simulate the result. What happens, ladies and gentlemen, if we plug 1,000 susceptibles in here, we have 0 infectives and 0 recovereds? What will happen? Suppose we have 1,000 people here susceptible and 0 infective, 0 recovered. What will happen? Nothing. Just stay susceptible, right? Right? There's just all remain over here. Because what? Because there ain't nobody to infect them. Well, that's how it might be expressed in Texas. But there's nobody to infect these susceptibles, right? So they just all say susceptible. I mean, in a symbolic sense, what's going on is that, S maybe 1,000, but I is 0. And well, okay, M is 0 here. I'm dealing with a situation with no immigration. I should have said that. Okay, so S dot is 0, and so it doesn't change. S doesn't change. There's no change in S. The rate of change is 0. Okay, great. So it just says all susceptible. Now let's suppose we start one person in the infective state and nobody susceptible and nobody recovered. Then what happens, ladies and gentlemen?
The infected person will eventually recover.
They'll recover. And how many 1,000 people get infected? It's a bit of a trick question. Remember, 0 people start here, 1 in infective, 1 and 0 in recovered. So how many people get infected? 0. Okay, ladies and gentlemen. So we might think we can decompose into those pieces, but we will be sorely mistaken. This is, of course, the behavior we saw last time. Number of susceptibles plunges, the number of infectives rises, and the number of recovers rise. The behavior here of the combined scenario where we have susceptibles and infectives together is just extremely different. Night and day difference from the situations where we have just susceptibles, just infectives, and summing them together. Do people get that? You can't separate them out in that way. Now, ladies and gentlemen, this has very significant implications because it's only when we have this linear property and variations of it, like when we transform things and then have a linear system, it's only then that we can really reason about the whole based on the parts independently. It's only then we know how to take apart the pieces. We can analyze them with respect to comfortable, simple situations and then sum up the results. Here, the behavior of the whole is greater than the sum of the parts. And what this means is, in terms of our decision making, we can't simply say, let's analyze this policy in isolation. Let's analyze this policy in isolation. And then we know what the result is of combining them. No, you got to simulate them together. If you have different decisions you can make, and you want to consider the impact of taking them as a package, it's going to be different than if you consider them independently as solitudes. So when I said last time that with linearity, we can take the pieces apart and figure out the response of the system to those pieces and then sum them together. This is one example of that. And with a linear system, it works fine. With a nonlinear system, it just doesn't work. Does that make sense? And it's reflected in a symbolic way in this fact that we have this interaction term, S times I. Because in our model, they, ladies and gentlemen, interact. They contribute to this force of infection that affects susceptibles is contributed to by the infectives. Not just the number of susceptibles, but also the number of infectives. Does that make sense? Okay. Okay, so with those comments being in mind for susceptibles, I'd like to talk now more about these models. So you explain these various quantities with them, and we walk through the basic intuition here. We talked about the force of infection, and it's the fact that it's a likely density, it's a chance per unit time of infection. One thing it bears noting is we can think about that term of the number of people per unit time being infected in one of two ways. We can think about it as, okay, from the standpoint of a susceptible, I'm a given susceptible, how many people do I run into total per unit time? What fraction of those people are infective? And for each of those contacts between me and one of those infectives, what's the chance of transmission? And then finally, that's my chance as a single susceptible for getting infected. And then finally, how many susceptibles are there? And you can piece together the system like that. So then we get sort of S times this force of infection term, right? We comfortable with that? Okay. Alternatively, we could think about it from the perspective of an infective. I'm a given infective. I'm on the prowl. And I can spread the infection. How many people do I run into per day? What fraction of them are they susceptible? So here we have I'm a given infective. I have C contacts with anyone. Of those, S over N fraction are susceptible. So I've contacted 100 people per day. 50% of them are susceptible. For each of those chances, I have a chance beta of transmitting the infection, right? And in fact, if we multiply that, C times S over N times beta, that gives, for me as an infective, it gives the number of people, the average number of people I'm infecting per unit time. So, okay, each of those 50 people, I have a 4% chance of infecting, say. So on average, I infect a 4% chance per contact with those 50 contacts per unit time. So I infect, on average, 2 people per unit time. That's just another way of looking at the term, sort of just rearranging it and thinking about it this other way. This is going to be key to understand for our discussion in another 5 or 10 minutes, okay? This other perspective. Because this gives the clue for why things start to slow down in terms of us infecting people. Because it becomes harder and harder and harder as me as an infective to spread the infection over time. Why?
Force of infection goes down.
The force of infection actually is rising. That's the interesting thing. But what's going down? It's related to that. The number of susceptibles. So, I may be circulating among just as many people, but more and more of those people around me I can't infect anymore. So I'm becoming less and less efficient in spreading this infection. Okay? As the number of susceptibles falls, the number of susceptibles surrounding each infective falls, and the rate of new infection falls. I can't spread this fire to more and more things, because more and more things around me are charred. They've already been infected. They're already recovered in some cases, potentially. And so I have to work harder and harder to spread the infection. And that's going to be the critical throttle, the fraction susceptible around me. And ladies and gentlemen, that starts to be why you can achieve herd immunity. Because if you can bring down the number of people around a given person who has measles to a low enough point, maybe by bad luck they'll infect 1 or 2 people, but there's this buffer that prevents it from spreading. It makes it very inefficient to spread. It's unlikely to be able to spread around the population. Okay, so let's talk about that. Right. I think I'll come back to this point. I want to hit on this point. So we saw, ladies and gentlemen, this basic dynamics of the spread of infection. And again, this applies to spread of consumer products. It applies to spread of rumors. It applies to spread of political ideologies, what have you. In many cases where you see the same basic SIR type of situation. Here we have a situation where we have some number of people. They're largely initially susceptible. We have, some number of individuals. I think I started here for reasons that are not totally, I don't remember this exactly, but we had some initial recoveries. And then we have basically very, very few initial infectives. But we have somebody. Okay. So what we have here in the red is the number of infectives. It rises and it declines, right? And we're going to be reasoning about why this is based on stocks and flows. And it's an extremely useful and powerful perspective. So what's going on here? What's going on at these different phases of this infection? Let's reason through. So early on, what do you think's happening? Think about this situation. Give to me some understanding. Why do we see this number of infectives rise so quickly? Consider the very first infective.
There's a lot of susceptible people.
Great. There's a lot of susceptibles around them. You know, every time they sneeze, cough, what have you, there may be, a bunch of people around them, and half of them may get infected. And again, it goes up exponentially. You see this rising exponentially? And if you go analyze the underlying math, you'll see why that is. Essentially, it's like a situation where you have close to that initial point. It's like where you have I dot equals some coefficient. I'll call it epsilon times I, and this tends to lead to an e to the epsilon t. And this is exponential growth. So you see that exponential, whoa, that doesn't look exponential. Exponential growth over time. One person infects two people. Each of those infect another 2, therefore it goes to 4, to 8, to 16. You get this doubling over, and while there's lots of susceptibles around, that's very sustainable. And what happens to the number of susceptibles as a result? It's dropping very, very quickly. So initially, that's what's going on. Initially, each infective infects, just about everyone around them is susceptible. So they infect something like C times beta people on average per unit time. Say per day, they're mixing with 100 people, and of them, 100% are susceptible. And each of those 100 people, they have a 4% chance of spreading the infection. On average, they're infecting how many people per unit time? 4, right? 100 times 100% times 0.04. 4 people per unit time. The rate of recoveries right now is 0. Basically, no one's recovering. Why? Why is no one recovering initially? For the very initial period. Nobody's infected. There's only one person infected, and they haven't transitioned yet. Okay, now, in the short term, the number of infected grows very quickly. It's doubling over because of that. And it turns out in the underlying mathematics, that's going to, it results from this. So we have C times beta times I. I dot equals C times beta times I. I put it as epsilon, and I could write it out here. Very close to when S over N is close to 1, is approximately 1. We have C times beta being epsilon, so we have I dot equals C beta times I. So we get this this positive feedback, okay? So it's growing. Susceptible starts to decline, but it's still high enough that each infective is surrounded overwhelmingly by susceptibles, okay? Okay, so then what happens over time? Well, it stops growing exponentially. This is initial exponential growth, but that starts to be tapered. Why? Well, there's fewer and fewer susceptibles around. So they're still spreading the infection, but they're spreading it less efficiently. Now, instead of having I is ineffective having 100 people per unit time, and 100 susceptibles per unit time I'm running into, I have 50 per unit time that I'm running into, because half of the people around me are already infected, potentially recovered. There starts to be recovers at this point, so that also draws down I, right? If the recoveries, if there start to be recovered, it'll also draw down I, right? So I's rising. Why is it rising from a stock and flow perspective? If I's rising, what does it mean? Yeah, incidence is greater than recovery. The inflow is greater than the outflow. So there's more people coming in here than are going out, but this is starting to pick up. And this is starting to get less fast than it was before, because for each of these folks, there's more and more people around who are susceptible. Fewer and fewer people around who are susceptible. So this inflow is declining, this outflow is increasing, and so I isn't rising as quickly. Now, at some point, ladies and gentlemen, there's going to be a plateau. There's going to be a tipping point. This point here. What is going on at that point? Give me one thing from an aggregate perspective that has to be the case. If the number of infectives is flat, it's not going up, it's not going down. What does that tell us from a stock and flow perspective? Sorry? Inflow equals outflow. This equals this, right? So the rate of incidence is equal to the rate of recovery. That's a key place. After that point, a lot of interesting things will start accelerating in the system downward. So rate of recoveries equals the rate of infections, right? Okay. Now that's good. So we have a maximum and the number of infectives here. Now, this may be counterintuitive, because remember, there's lots of things going on. You might think, gosh, with a maximum the number of infectives, shouldn't the number of infections, the rate of infections, people per unit time getting infected be at its highest? Well, it could actually be at its highest there, but the point is that we have a lot of people recovering too, so it's plateaued out. But from another perspective, from an individual perspective, this is key, and I expect you to know this. This is key. Another thing that occurs at this peak, another way of viewing it, is that each infective infects exactly one other person before recovering. In other words, I as an infective infect just enough people to replace just me. It's under that condition that when I recover, that the number of people infective will stay constant, right? If I nominate a replacement for me, every time I recover, there's one person who steps in for me, then it's at that point that it will stay constant, right? The number of infectives will then plateau. It will stay constant. So from an aggregate perspective, at that peak, ladies and gentlemen, the number of infections, the rate of infections equals the rate of recoveries. On the other hand, at that peak also, the number of people infected by a given infective over the lifetime of the illness is one. They nominate one person. That's all. If they nominated two, if I replaced myself by two people, it would be going up, right? If I replaced myself by only half a person, it would be going down. It's at that point that it equals one. we say the effective reproductive number is 1. In other words, I'm infecting only one person over the course of my illness. And we call that the effective reproductive number. R star. That's how it's written. R star. That's the classic term for it. Okay? So it's at that point, it equals that. Now, ladies and gentlemen, I will submit it as a puzzle to you and solicit your insights. Why does the number of infectives now fall? And why does it fall so relatively precipitously? Why is it dropping like that? There's several reasons behind it. Give me one reason.
It's a high number of infections.
Good. And why does that lead it to drop? Because they're recovering. Good. So they're recovering. So there's lots of people to recover. That first order delay associated with recovery from this has a really big stock here, so they start piling out, right? So that's great. It starts being drawn down because of that. Why else does it start? So we've said the outflow is very large here because this is at its peak. This flow will be at its peak, right? It will start flowing out really quickly. Why else might I be decreasing other than this flow being very high? The incidence could be getting smaller. Why would the incidence be getting smaller? There's fewer susceptibles over time. The susceptibles are still dropping, right? At this peak, the susceptibles are still dropping fast, right? So there's fewer and fewer people to get sick, right? Why else might it be dropping quickly, though? I heard a voice that I know. Don't tell people I've been hearing voices. I thought I heard a voice from this very audience that mentioned something else besides the number of susceptibles. What else is happening after this peak that might accelerate its downwards peak? So the inflow to the number of infectives, why else might it be declining? The number of susceptibles is declining. What else is declining that contributes to the incidence? Sorry?
The effective contact.
The infectives, yeah. The number of infectives is declining, and that drives it even lower, right? If the number of infectives is declining, that takes maybe a bit to wrap your head around. Okay, the stock value is declining. Because the stock value is declining, the inflow to that stock is going to decline. Because the value, how quickly people are coming in, depends on the stock, right? So now the stock is declining, and the inflow is now going to be declining as well because of that. Because there's fewer contacts with susceptibles, both because there's fewer susceptibles and fewer infectives. There's fewer contacts with susceptibles, so the inflow is going to be declining. So, ladies and gentlemen, this downwards decline here is driven by two things. It's driven, you could argue even three things. It's driven by a high rate of outflow here. It's also driven by a declining number of susceptibles. It's also driven by a declining number of infectives. And all those contribute to a declining number of infectives. This is a feedback, right? The lower it goes, the faster it's going to be driving itself even lower. And so you see this declining quickly here, and it's declining for all those reasons, okay? And it's declining down, and it declines basically to extinction in terms of the number of infectives. Now, the number of susceptibles, by contrast, does not decline to extinction. Why? Well, the number of susceptibles after a long period of time is constant here, and it's not zero. Why? We talked about it, we alluded to it last time, and this should help you understand why.
Does the probability of transmission decline?
Yeah, I mean, whatever infectives are around, they're so inefficient transmitting. There's just no way they're going to cause some sort of outbreak. So there can be plenty of susceptibles going around, and their chance of bumping into the infection is not sustaining. It's not self-sustaining. It's it's drowning itself out. There's not fuel enough to keep the fire going, so it's just disappearing in the population. And there's some lucky susceptibles who never got infected, and there may be a few infectives around, but they're not really a danger because they're surrounded by so many people that can't get infected. They're likely to recover before ever infecting anyone, right? And therefore it just peters out. Those couple people, it just drives it down exponentially, essentially to zero. Okay? So this is the stock and flow feedbacks associated with these characteristic curves. And it's useful to view it at an aggregate level, and it's useful to view it at an individual level. To put on that persona of an infective or of a susceptible, think about what's going on. As an infective, it starts being very easy to infect people. Over time, it becomes harder and harder as there are fewer susceptibles around. More and more likely to recover, less and less likely to pass it on, less and less likely to be able to replace myself by a susceptible who's gotten infected before I recover. From the perspective of the susceptible, early on, there's very few infectives to worry about, but over time, more and more infectives, I'm more and more likely to get infected. But if I can make it past this peak, the number of infectives starts dropping really rapidly for those three reasons. Lots of people recovering, fewer and fewer susceptibles available to infect, fewer and fewer infectives to infect them. And so I may survive well beyond that time if I can make it to that peak. The worst is past. By the time of the flu peak, the worst is past in terms of getting infected. That seems counterintuitive. You would think, at the time of that flu peak, the bulk of the infections are about to occur. Well, look at the situation here. It'll differ some for different time delays involved in particular infections. But by that point, the number of susceptibles is often low enough that those many people that are infective just aren't going to be nearly as effective spreading the infection as those earlier on, when the numbers were less. Does that make sense? Okay. So let's okay. Yeah, this is kind of an interesting thing. So the maximum value of the stock of infectives is actually in general going to occur at a different time than the maximum of incidence. So the maximum of incidence depends on, the maximum number of people getting infected per day depends on both number of susceptibles and force of infection. The force of infection, and the number of infectives keeps rising as long as the incidence is greater than the recovery rate. It may be that the highest force of infection, the highest chance per unit time of getting infected, and the maximum of the incidence, the maximum of the incidence is going to be higher. The maximum in terms of the number of people recovering or getting infected per day may occur earlier before that peak in the number of infectives. So let's talk about how this relates to a causal loop diagram. So we can diagram a system like this using a causal loop diagram. So here we have a number of susceptibles, a number of infectives, a number of here I put down their new recoveries. And what happens here is the number of susceptibles, as the number of susceptibles rises, the number of contacts between susceptibles and infectives rise, right? And as the number of infectives rise, that is a plus, it just doesn't show up well. The number of contacts also rise. So there's a positive feedback occurring early on here. We can think of what's going on early on as being associated with that initial feedback between infectives leading to more number of infectives. As that rises, the number of contacts rises, leads to more infectives. and you've got this vicious cycle spreading the number of infectives, right? So you can think of that component of the feedback as dominating early on. However, what happens over time is that another feedback starts balancing this, starts exerting control. What other feedback would exert control here? As the number of new infections rises, what else happens that dampens this feedback? Okay, so there's a recovery component, but the number of susceptibles is often the more immediate thing that affects it. So that's what makes it less and less efficient in terms of the number of contacts between susceptibles and infectives. So as this feedback is going on, this feedback is the fastest one, but this one starts to play a role. So we could kind of diagram this out, that early on this feedback is dominant, and then this feedback starts to play a big role in plateauing it. There's fewer and fewer infectives, and then later on it's more the recovery that's going on. Down in this region, ladies and gentlemen, after this peak, the number of infections taking place is quite a lot smaller often than the number of recoveries. So what dominates the dynamics, what dominates the slope of this here, this kind of decay, does this look like something to you? This decay here, where have you seen that sort of decay before? Sorry? Okay, it can, you can see that in a logarithmic context, but we've actually seen it with a certain type of causal loop diagram or a certain type of building block.
Inverse exponential.
Yes, it's like e to the minus alpha t. And where do we see that? Where do we see an e to the minus alpha t? What building block of building up stock and flow diagrams has this sort of behavior? It drains itself, and as it drains, initially it drains really quickly, and then it drains more slowly because there's less things to drain. It's a negative feedback loop associated with a first order delay, right? So we have a situation here where we have a stock X, and we have some chance per unit time of progressing down this, right? And we can express this as X times alpha. Alternatively, we could express this as some mean time in this stock, and this is X over mu, right? We saw that? Two different ways to view that. Remember that? Remember? Here, the rate of flow is proportional to the stock. Stock is high, flow is high. Stock is low, flow is low. And I actually wrote the formula for it for those who are so inclined. X dot equals alpha x, right? Minus alpha x. Why the minus?
It's draining.
Because it's draining, it's flowing out of it. So the bigger alpha x is, the faster the rate of decline of x. Or we can express it as x dot equals minus x over mu. And ladies and gentlemen, the solution to this equation goes as this. It's some initial number x0, the number of people there originally, times e to the minus alpha t. Ladies and gentlemen, this decline here is nothing more than less than the characteristic decline associated with this first order delay. This stock is draining, and it's draining at this rate. I remember one health conference I was at where someone was showing graphs of H1N1 cases from across Canada, and he mentioned, it's really interesting. In all these different provinces, all these provinces across Canada, you see the same basic rate of decline of the number of infectives over time. If you plot it out, they're declining at the same rate. And ladies and gentlemen, that's why. It's because it's a first order delay. You have this chance time of recovery, right, or mean time with the disease, and this is associated with recovery. It's associated with that process of recovery out of here. That's what explains those common patterns within that data. So this is sort of a recovery-driven process, and it's that part of the loop that's executed there. Now, I've drawn this heuristically with these loops. There's actually software that will analyze causal loop diagrams and show sort of which loop is dominant. So their causal loop diagrams linked to a underlying stock and flow model, and using the underlying differential equations, you can actually get it so it'll show which loops are currently dominant. And what you'll find is in nonlinear systems, that dominance shifts. So in other words, at certain times, certain loops may be dominating, at other times, different loops will be dominating, and there's a shifting loop dominance as the system plays out over time. Okay. So that was some explanation of why we see these sort of dynamics. Okay, now I'd like to pose to you a little challenge. My challenge would be as follows. First of all, we built up this model last time in the context of Benson. I would like you to do it in any logic for next time. So build up the same model we built in Benson. Do it instead in any logic, okay? Secondly, I would like you to expand this model with two features. Feature one, I would like you to expand it with a new stock, and that stock will be a vaccination stock. Stock where people have been vaccinated. And I want you to think, imagine that we assume that vaccination confers immunity to infection. People are not infected anymore. How would we add that to the diagram? Well, in this case, we'll assume that they're circulating in the population, so they're part of that denominator, I over N, where N is the population. That would be no longer S plus I plus R, but S plus I plus R plus V, the number of vaccinated people. That's one way in which it impacts things. But they're not subject to infection. It's just only susceptibles are subject to infection. And we want to see the effect of starting a different fraction of that population initially vaccinated. So we want to see what's the impact on the infection spread when 10% of the population is vaccinated, 20% versus 30% versus 50% vaccinated. See if you can do that. Have that separate stock and just have it, when it starts up, a certain fraction of the population is there, a certain fraction otherwise starts susceptible, one person starts infected. See if you can do that, okay? That's issue one.
Question.
Yes?
Should it be that the susceptible people are moving towards the vaccinated state?
Not yet, because we're just going to start them up in a vaccinated state. So
effectively, the vaccinated state, or the vaccinated stock, is utterly unlinked to the rest of the system.
It's currently it'll be unlinked. Later we may have this vaccination program that goes on. The reason that adds, that I'm not suggesting that immediately, because it adds sort of a race between the infection spread and like how quickly you can vaccinate. And if we just want to look at the herd immunity effects, like if you vaccinate enough people, it will lead the infection to not be able to have an outbreak. We need them to start vaccinated, okay? If you want to put a flow between them, that's great. You could have a per year chance of vaccination or something like that. That's great. It's just that we won't be depending on that mechanism initially.
Okay, so wouldn't this model just be equivalent to say, like, okay, we're considering 1,000 people, 999 of which are susceptible.
Yes.
One of which is infected.
And the rest are recovered, you're saying?
No, and 0 are recovered.
Okay.
Now we move that to the model where there's vaccinated. Let's say half of all people are vaccinated, so vaccinated has 500. Now susceptible has 499.
That's right.
And infected has 1.
That's right.
Is that that not equivalent to a system where vaccinated doesn't exist, and susceptible is just 499?
It's not equivalent, and there's a key reason why.
Why not? Where is the link between vaccinated and
The total population lowers the prevalence of infection.
That's the issue. It's the total population. The denominator is much bigger. Imagine a situation where 99% of the population is vaccinated. Now you've got this huge denominator that's diluting the effects of those susceptible. So around each infected, there's still some susceptible circulating. The vast majority of people that they come into contact with are not susceptible, so they can't spread it efficiently. So that's why it's not. It's a great question, but it turns out it's not the same because of that issue. We have that I over N, the total population size, and V, it's S plus I plus R plus V, not just S plus I plus R. Does that make sense? Yeah. Okay, great question. So that would be challenge 1. Challenge 2, ladies and gentlemen, would be I would like you to add in to that model. You can make it so 0 people start vaccinating for this part. I'd actually like you to add in a birth rate and a death rate, where the deaths occur from any stock with the same likelihood. So we're not simulating a particularly virulent infection where people die only if they're infected. Instead, every stock has that same chance of mortality. So it's something more mild, say like a mild case of flu for people with strong immune systems. And so there's a mortality rate and a birth rate, and those can be the same. Make them, 2% per year, something like that, and see how that affects the infection dynamics. Let me pose that as a question, a little challenge now, to reason through. How do you think? So what we've just looked at here, ladies and gentlemen, what we've just looked at is infection in a closed population. What do I mean by a closed population? Anyone? It's a closed system. There's no one dying, no one coming in. Fixed population size. Suppose now we were to have population turnover. People coming in and leaving. How would that affect things? People are born in a susceptible state. Yes, we'll assume that. So how will that affect things? The plot thickens. So how will that affect things? Here, what do the susceptibles do? Does it ever go up here? Number of susceptibles go up somewhere along here? No, it's only drawing down. Why? Because we're only exercising, ignore this. We're only exercising these flows. There's only, the only thing coming out is an outflow of susceptibles. Now we have an inflow. How does that change things?
If the birth rate is greater than the contraction rate, then it's going to go up. If it's less than, it sucks.
I hear some great reasoning. There's going to be some race almost between the spread of infection and the number of people coming in. But it turns out it's not quite that simple, but you're absolutely right that it's going to be tugged down by infection rates. It's going to be tugged up by birth. And no longer is it a situation like the wood is burning to a crisp purely in your fireplace. Instead, it's as if we're doing what to the fireplace? We're putting more wood into it and clearing away the old burnt wood. So that, ladies and gentlemen, I pose to you as a challenge. And that will take us to the cusp of agent-based modeling. We'll examine this in an aggregate model, and we'll then go on and soon examine it in an agent-based model. I'll examine an aggregate and then an agent-based model, potentially next week, if necessary later. Okay, so any questions about that before we break? Yes?
An interesting conclusion to the challenge would be to find the minimum birth rate where the infection never stops.
Okay,
So the fire keeps on burning because you're putting one on fast enough.
good. Where there's, right, where the steady state of the infection, instead of being 0 here, where it's going to 0, instead it stays at some non-zero rate. I like that. I like that. Okay, so what birth rate? And by the way, this is birth and death rate to keep things simple. So the population isn't growing purely over time. It's an interesting question. What would happen if birth were faster than death? And that's another whole sort of level of complexity. But the key thing is whether it's open or closed. And I like that idea. Okay, what birth rate would be sufficient to keep the infection endemic? That's the term that's used, right? We talk about an endemic infection that stays present in the population. What birth rate would give us that? What birth rate would lead to an infection not dying out but staying present? Troublesome prospect, isn't it? But now your model will have vaccination in it, so we'll be able to look at things that might drive it out of the population, even in the context of birth. And ladies and gentlemen, if we consider our broader population over longer periods of time, it is most certainly not a closed system. It's most certainly an open system. And so we'll be grappling with the sort of issues that, at least over longer time frames, confront us. For a very short time frame, for a fast-spreading infection, for the case of something like flu, compressed into a single season, we might ignore birth and death. For longer-term issues, infections that stay around, and even flu year to year, you're not going to be able to ignore births and deaths. You need to start including them. So I'll pose it as a challenge. Come back with that anti-logic model. Come back with your problems building that anti-logic model. And then we'll talk about some of the implications for herd immunity and for infection dynamics, contagion dynamics within an open population. Okay? So that's all for today. Thanks.
In the new set of lecture slides that you uploaded,
Yeah.
the 6th lecture, only the first page of it was uploaded for some reason.
Really? Okay. So it says like lecture 6.
Yeah, of the new lecture slides. Because I was looking for the term that you used for 1 over alpha. What symbol was that?
Oh, I probably used mu, but I'll upload that lecture.
Okay.
So and this was in the context of first order delay.
Yeah, it was for question 3 on the assignment, the first assignment, for deriving the expression for one of the derivations.
Okay. Yeah, I was probably, if it was 1 over alpha, my guess is I would have used mu, because mu is often used as like a time constant, but it's possible I used tau. Tau.
I think I remember tau.
Yeah. 1 over alpha. Yeah. So this is often used for time constants as well.
No, not much too loud.
Yeah.
I'm having trouble with the derivation part there.
My question as well.
I think part of my confusion is coming from not understanding when derivatives are used.
Okay.
And so looking at the equations that we were talking about today, it kind of made it seems a little bit more obvious that they should that stops should be derivatives in Vensim as opposed to numbers. So if you click on equation editor for prevalent cases,
Right.
it says